Organic compounds. The early chemists divided compounds into two broad categories, organic and inorganic. Compounds that they found from living organisms were called organic, and compounds from non-living organisms were called inorganic. So in chemistry, we use the term organic differently than they use it at the grocery store. Organic fruits and vegetables means they haven't been sprayed with pesticide. In chemistry, organic means that it basically contains carbon. So these organic compounds were easy to decompose, easier than the inorganic, but they were also hard to synthesize. They were hard to make. Easy to take apart, hard to put together. The inorganic compounds were easy to make, but hard to take apart. So today, we can make organic compounds in the lab, and we find them all around us. And in fact, your body is full of organic compounds. Organic compounds are composed of carbon and hydrogen. That's the hallmark of an organic compound. They can have other elements in them, but they're usually in small amounts. We can have oxygen, nitrogen, phosphorus, and sulfur. Those are pretty common. And there can be trace amounts of other elements. So carbon is the key to organic chemistry. Organic chemistry is a one-year course or 2 semesters of courses after you take Chem 1A and Chem 1B. So I'm just giving you a teeny tiny taste here of organic chemistry, and if you go on, then you'll learn probably more than you want to about organic chemistry. But this is methane. Methane is an organic molecule. It's just got carbon and hydrogen. Carbon bonds that we find in organic compounds are almost exclusively covalent. So carbon makes covalent bonds, doesn't make ions. Carbon always forms 4 covalent bonds, and we'll understand why it does that later. It can form single, double, or triple bonds. It can bond with itself, with other carbon atoms. It can also bond with other elements. And the chemistry here is unique because carbon can make long chains of carbon atoms. It can make branched structures, and it can make rings of carbon. And you can actually have multiple rings all bonded together. So carbon is really the basis of life. It's a part of all organic molecules. So here's some examples of carbon bonding. So here we've got 3 carbons in a chain with hydrogens around. And notice that each of these carbons has 4 bonds. Here there are 4 single bonds. Here's a compound called ethene. We've got 2 carbons and 4 hydrogens. Each of these carbons has 4 bonds. A double bond to the other carbon, and then 2 single bonds, so a total of 4. Here's an example with a triple bond. Here's carbon bonding to oxygens as well as to carbon. Here is a branched chain, and this is a cyclic compound where the carbons are playing ring around the rosy. So there's compounds, and we can divide them into inorganic compounds, which is what we're mostly studying in this class. We learned how to name molecular, ionic, and acids. And then we've got the organic compounds. Organic compounds are divided into 2 broad categories: hydrocarbons. My pointer's gone. Okay. Hydrocarbons and functionalized hydrocarbons, which is fancy hydrocarbons. They got extra things on them. Oh, you're going to be like that, are you? Oh, my iPad's messing up. So hydrocarbons contain only carbon and hydrogen. Hydrocarbon, hydrogen and carbon. Hydrocarbons make great fuels. So oils, gasoline, liquid propane, natural gas, these are all hydrocarbons. They burn really well. Hydrocarbons that only have single bonds are called alkanes. And if they have double bonds, they're called alkenes, and triple bonds are called alkynes. So the suffix ane, ene, or ein tells us what kind of bonds are present. Then there's a prefix well, I'm sorry, it's not really a prefix. The base name of the compound is determined by the number of carbon atoms. So the base name is the number of carbon atoms, and then the suffix -ane, -ene, or -ine tells us whether there's multiple bonds or not. The base names here, for the first 4, are strange. And then after that, it reverts to those prefixes that we learned before. Pent, 5, hex, hept, oct, non, dec. We just left the A's off. Okay, the first 3, though, are odd. Meth, eth, prop, and bute. And so how do you remember that? Well, Mom eats pickled bananas. I didn't know you could pickle bananas, but maybe you can't. Never, and anyway, this makes you think that Mom might be pregnant if she's eating pickled bananas. Meth, eth, prop, bute. 1, 2, 3, 4. And then the suffix -ane, -ene, or -ine. So we can have methane, ethane, propane, butane, pentane. We can have pentene. We can have pentyne. So here's some examples. Here we've got methane, 1 carbon, all single bonds. Propane, meth, eth, prop. Mom eats pickled. So propane is 3 carbons. 3 carbons in a line, and then their need for 4 bonds is made up with hydrogens. That's what's used in your grill outside. N-butane, butane has 4 carbons. So here we've got 4 carbons, and again, hydrogens make up the bonds for the other carbons. Common fuel in Bic lighters, right? Pentane, 5 carbons. That's in gasoline. Ethene. Eth means 2 carbons. The ene means there's a double bond. So ethene, the double bond would have to be between the 2 carbons, and then there's 2 hydrogens. This actually is a gas that helps fruit to ripen. And it is naturally occurring, but you can also add it and cause your fruit to ripen. It's a gas. Ethyne, 2 carbons again, but the ine tells us it's a triple bond. And this is a fuel used for welding torches. A functional group, the functionalized hydrocarbons, mean they have a special group, a special atom or group of atoms that gives them a different function. So it imparts a special character to that organic compound. You can also argue that double and triple bonds are functional groups. So we put these organic compounds into families, and the thing they have in common is that they have the same functional group. So methanol and propanol, methanol and isopropanol are both members of the alcohol family. So here's methanol, and this is isopropanol. And the OH group, that's the functional group. That's what makes it an alcohol. So methanol is different than methane because instead of the hydrogen there, it's got an OH group. And so it has different properties and will undergo different reactions. So these are the categories. Alcohols have an OH group, and the names are derived from the different functional groups. And again, it's actually a little difficult to talk about this because I have to keep it way, way on the surface. So really, what do you need to know about all of this? You need to be able to name straight chain alkanes. So based on the, if it's got 5 carbons, it's pentane. If I showed you a picture of something with a double bond, then you should be able to count the carbons and put the ene ending on it. I'm not going to make you do any of these, but I want you to have heard about them so that if you saw them, you could say, oh, that's one of those organic functional groups. I could go look it up. Ethers have an oxygen in the middle here. There's aldehydes and ketones and carboxylic acids, esters, and amines. And these are all things that we encounter in our everyday lives. These are the different families of organic compounds. There are lots of different aldehydes. There are lots of different ketones. So let's draw the structural formula for nonane. So nonane, the initial part of the name is known. How many carbons would that be? 9 carbons. So because we're not given any other information, we'll just put them in a straight line. So there's 2, 3, 4, 5, 6, 7, 8, 9. This is the kind of math that you end up doing in organic chemistry. It's a lot of counting. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then each of these carbons needs to have 4 bonds. Because this is only single bonds, they're each going to have 4 single bonds. And what we put on there to make those bonds is hydrogen. So you can see how drawing these out can get a bit tedious. I should probably change this example so I don't have to do all of these. This is what's called a structural formula. And if I wanted the molecular formula, what would it be? You'd have to count those all up, wouldn't you? C9, H something. Well, each of these carbons has 2 hydrogens on it, and then we've got 2 extras at the end, 1 here and 1 there. So it's 20. It's 2 times 9 plus 2, H20. But this is the structural formula. Any questions? What family does this compound belong to? I would not expect you to do that on an exam, but if you had the table, so what's different about this? It's got this thing here, right? The carbon double bonded to the oxygen. So we'll go back to the table and see if we can find something like that. Well, all of these have oxygen double bonded to carbon. Then we have to look at, well, what else is going on down here? So this R we just use for alkane, CH3 or CH, any group like that. So this has carbon on one side and oxygen on the other. Well, that's not what we've got here, right? Here we have this carbon with the double bond to the oxygen is between 2 other carbons. So that's what we need to find. So here, now this is oxygen. This looks good. This one's not right because this is a hydrogen. So it's this guy right here. So this belongs to the ketone family. Any questions?